Hey everyone, welcome back. Today we're diving into a fascinating breakthrough in AI. How autonomous vehicles predict pedestrian behavior with unprecedented accuracy. Imagine a self-driving car that doesn't just see a person on the sidewalk. It anticipates whether they'll cross the street, where they'll go, and how to react. That's the power of the TA-STGCN model we're exploring today. Let's break it down. So why is this even a problem? Current self-driving systems struggle to predict pedestrian intent because they often ignore critical context. Think of it like a driver who only watches the road ahead but ignores traffic lights, crosswalks, or even the size of a pedestrian's bounding box in video footage. These clues matter. A person near a red light behaves differently than one near a green light. A pedestrian pausing at a crosswalk might be waiting for a gap in traffic. Traditional models miss these patterns, leading to less safe decisions. Enter TA-STGCN, a smarter system that treats the road like a dynamic puzzle. It doesn't just track where people are, it maps how they move, connects them to traffic elements like lights and crosswalks, and uses AI to spot hidden patterns. Let's unpack how it works. At its core, TA-STGCN uses a spatio-temporal graph, a dynamic map that tracks both location and time. This graph has two types of nodes: pedestrians and traffic elements, cars, lights, crosswalks. The connections between them, called interactions, are key. For example, a pedestrian near a red light creates a different interaction than one near a green light. Over time, these relationships teach the model how pedestrians behave in different scenarios. But how does it learn these patterns? The model starts by extracting features from each node. For pedestrians, it uses a convolutional neural network, CNN, to analyze their position, speed, and the size of their bounding box. Bigger boxes mean closer proximity to vehicles, critical for predicting crossing intent. For traffic signs, it reads the sign's type, stop, yield, its state, red, green, and location. This mix of data helps the AI connect the dots between a pedestrian's actions and the traffic environment. Now here's where it gets really smart. TA-STGCN uses two neural networks to process this data. First, graph convolutional networks, GCNs, analyze spatial relationships, like how a pedestrian interacts with nearby cars or signs. Then temporal convolutional networks, TCNs, track how these interactions evolve over time. Imagine watching a video clip. The GCN checks who's where, and the TCN sees how their movements change frame by frame. Together, they create a rich picture of the scene. The model's brain also includes a spatio-temporal graph layer with three key components. 1. Feature convolution to dig deeper into the data. 2. Spatial message passing to share info between nearby nodes, like pedestrians and traffic lights. 3. Temporal message passing to track short-term changes. Finally, all this data flows into an LSTM, a type of neural network good at remembering sequences, which predicts the pedestrian's intention, like whether they'll cross the street. So how did it perform? The researchers tested it on the Pi dataset, which has 6 hours of real-world driving videos. The results: TA-STGCN achieved 84.65% accuracy, a 4.75% improvement over older methods. Metrics like ADE, average prediction error, and FDE, final error, were also significantly lower, meaning the model's predictions were more precise. But here's the kicker. When the model was given traffic sign data, like whether a light was red or green, it got even better. Component analysis showed improvements in every metric, proving that context matters. A pedestrian near a green light. Probably crossing. Near a red light. Probably waiting. The model learns these cues, making it smarter than ever. Of course, no model is perfect. Right now, it relies on pre-annotated data, which isn't practical for real-time use. Future work will focus on making it faster and more adaptable to messy, real-world conditions. But the potential is huge. Imagine safer self-driving cars, smarter traffic systems, or even AI that helps prevent accidents. So what's the takeaway? By combining spatial awareness, temporal tracking, and real-world context, TA-STGCN is a game changer. It's not just about seeing the road, it's about understanding it. Thanks for watching. If you found this interesting, hit that like button and subscribe for more deep dives into AI and robotics. And let me know in the comments, what other tech topics should we explore? See you next time.